It's with pleasure that I introduce to you Karen Worth. She is a faculty member at Wheelock College, and she has been there for 30 years. At Wheelock, about 30 years? At least 30 years.
That's enough.
And she has been working extensively in the area of early childhood science education. A couple of the things that she's well known for and has put a lot of time in are grants, research projects with the National Science Foundation. Recently funded project is Connecting Science and Literacy, professional development program for elementary teachers. In addition, she is an author of the Toolkit for Early Childhood Science Education, and has been working in several consortiums with the Boston Public School System to improve science education in the early grades. I believe pre-K up through 12?
No.
What is the high end?
Up through elementary.
Up through elementary school.
Don't believe in them after that.
I don't blame you, so we're all here for early childhood. Let's see, some of the other things she's worked on, which I found particularly interesting, were working with Boston Children's Museum, Chicago Children's Museum, and the Bay Area Discovery Museum in Sausalito. And she's also worked with public television stations on curriculum for early childhood programming like Curious George and The Cat in the Hat knows all about that. So some fun opportunities there. And has also worked with the National Academy and the Smithsonian Institution and several other national museums. So today she's going to talk with us about infusing science education into our early childhood curriculum. So I'd like to introduce Karen Worth.
Thank you. Thank you. Delighted to be here. And I was just muttering to my colleagues here that it's wonderful to see as many students here as I think are. How many of you are students? Wonderful. And how many of you are early childhood teachers? Or maybe you're both, right? I recognize that crew back there. And then I think there are a smattering of other people, but it's really delightful and to share some of my ideas about a subject that I'm quite enthusiastic about, you'll see. What I thought I'd do is I'd have a presentation I'll run through, but I also enjoy having people ask questions, not too many, and if you have either a question or a comment, you probably won't do this, but I encourage you to raise your hand and join in the conversation. There'll be time for questions afterwards, but I always like to be interrupted, but it doesn't happen very often. So just to get us on the right track, a few images. You have to remember we are talking about children, and I'll come back to some of these images later on, but I just like to be sure we know where we are, which is we're in early childhood classrooms. We probably should know this already, but I think it's important to think carefully about why science for young children. Science is not that present in young children in the classrooms, early childhood classrooms. So it's part of our responsibility as teachers or as students going into teaching to be clear, to become advocates for science for young kids. And I'll go into more why I think so, and hopefully you'll think so too a little bit. But I think the first place to start is to say, why bother? Why are we going to do science with young children? We've got so much to do in the early childhood classroom anyway. Why science? So to start with, it builds on this curiosity and interest that is natural to young kids. They are by nature curious. Any of you who are working in classrooms know that, or who have contact with little ones, is that they want to know about the world. They're curious. They're constantly asking questions, and they want to make sense of the world that they live in. They want to understand and be able to predict what happens. So we've got a starting place. Can I run my own computer? No. This you're not supposed to read, and you probably can't read it because it's so small on the handout. But it's also, I think, important for us to be sure that we have some connection to some of the research that's out there. This happens to be a quote, and I'll just pick out the piece that I think is important. It's from Eager to Learn, Educating Our Preschoolers, which was a research synthesis that the National Academy of Science put together a few years ago. And the part that I was delighted with is that statement says that they were looking at math. There's a lot of research in the development of language, math, and science because these appear to be privileged domains. That is, domains in which children have a natural proclivity to learn, experiment, and explore. So kids are doing this. We don't have to make them interested in exploring the natural world. They do this naturally. It also provides opportunities for children to engage in really cognitively challenging and motivating learning experiences. When kids start to explore what's out there, the natural world, the physical world, it's quite challenging. They're asking questions. How does this work? What would happen if? What if I do that? Does this always happen? And this both, again, motivating, but they're also very challenging, and that's part of what we're doing in early childhood is we really want to challenge children's thinking processes. They're already engaged. This lets us keep going. Another research synthesis published not too long ago is taking science to school K through 8. Well, no, we're talking about preschool, but one of the interesting things that this particular book does, and it's look at the research, the authors of the book said, we need to know what happens before kindergarten if we are going to talk about kindergarten through 8th grade. What do children come to kindergarten with? And again, probably not surprising necessarily to those of you who work with young children, but for this group at least, this interesting statement, research shows that children's thinking is surprisingly sophisticated and that they use a wide range of reasoning processes. We sometimes think they're totally bound to the physical world and what kind of thinking do they really do? Well, they're pretty sophisticated in their thinking. They have theories about how things work. They may not be right, but they do have theories about how things work. One of the examples that I was sharing with some people today is a very typical and frequent response of a 3-year-old approximately to, or 4-year-old to the question of where does the wind come from? It comes from the leaves. Because every time they have wind, the leaves are rustling. So clearly it's the leaves making the wind. Now that's not right, but it's very reasonable. It's their experience, from their experience over and over again, they reason and make a theory that the wind is created by those leaves. So we as teachers, we need to use that. We need to broaden the experience, but we need to acknowledge the sophistication of their thinking. They can use a wide range of reasoning processes. This comes again from this research. They have a lot of knowledge about how the world works. I was observing in an infant toddler classroom this morning over at the lab school, and those children know a lot about the world starting very young in their own inimitable way. And they're not just concrete and simplistic. They really, as say, they are theory makers. So, and this says before coming to school, and of course the before coming to school is what we all do. We have them before they get into formal schooling. Oop, wrong way. So it also, in preschool, we're building a foundation for the development of important STEM. I meant to change that to science. I thought I did, but I'll leave it as STEM. Science, technology, engineering, and mathematics. It's become a word. But when we give them those experiences in the preschool period, those preschool years, we're actually starting their science learning, their movement towards a understanding of some very basic concepts in science. We need to do that. It doesn't all happen in high school or middle school. It happens when they're 2, 3, 4, and 5. And it also, another reason for science, is that it gives us the opportunity for developing these important language, social, and physical skills, which we're supposed to do, in an authentic context, in a context that they enjoy, that they're motivated by, that they're interested in. So lots of reasons to do this, lots of reasons. Thus we should. I don't want to use that one. I'm going to keep going. So when I say science, what do I mean? And that's what I want to talk a little bit about now, just to give you a sense from where I about where I come from when I think about science and what that is. Because it's not just any science. I'm talking about inquiry-based science, and I'll talk a little more about that I think has all those values. We're not trying to teach them information. We're not trying to teach them the content, the specific content of science. We're trying to give them an opportunity to work on the thinking and reasoning processes, to work on carefully selected concepts and topics, and to learn certain basic skills. So what is that? What do we mean by that, and what does that look like? This is hard to read up there. It's even harder to read on your sheet of paper. But I'll use it anyway. Where I start in thinking about what is the nature of this kind of science is asking, what is it that scientists do? What is the process of knowing that scientists do? And I know we have at least one scientist in the audience who can correct me. But it is a process of inquiry, and I call it an inquiry learning cycle. There are others. Other people have worked on learning cycles. And what this does is give a little bit of a structure or scaffold to that process of understanding a science concept or science idea. And it starts with, you can see at the top, engage, notice, wonder, and question. When kids get interested in something, when we decide we want to give them a set of materials, for example, the water table, or balls and ramps, or studying snails and worms, or whatever it is, or living creatures, the starting point, as with science, is in simply exploring and playing with that phenomenon. Just getting a sense, what is it? What is it like? What does this thing do? What happens if I go this way? I wonder what questions I have. In little ones' minds, it may all be through, of course, behavior, not through language, but nonetheless, they're actually becoming acquainted with it on a very physical level. They do that naturally, and that happens a lot in our classrooms. If we want to move further, if we want to make it cognitively challenging, if we want them to go deeper, at some point we look at what they're doing, and we say, what are some of the questions they're exploring? What is it that we could actually pursue? Not just this broad interaction with the stuff and the materials, but where can we go with this? How do those snails move? A question that came up in one classroom I'll show you. Or I wonder if I can get the water to move from this water table down to the bucket on the floor. And you can think of other questions. You then enter in science once you have your question, and it may be the child's question, it may be your question. It may come from what you've observed, it may come from what you've heard. You then move into a more focused exploration investigation. Now it's not the broad scope of anything goes, speculation, wondering, questioning. That's still there. But now we're going to focus in on that question or that problem. And you can plan a little bit. That planning may be very much intuitive and not something that we notice or do formally. You may then observe closely. I'm going to put these snails on the surface, and I'm going to watch how they move. I'm going to think about it. You start to collect data, even the little ones, maybe just again in their heads, but they're collecting it through experience. You're going to think about that, talk about it with your little colleagues, your little friends, as well as through the teacher's facilitation and interaction. And you're going to keep going, looking more and more deeply at the behavior of these little animals, the behavior of water, the behavior of how structures stand up, whatever the concept is that's the focus. And then at some point, you're going to say, I think I know something now. I think I can say something, and I can share, discuss, and draw some conclusions with a group. So with the very, very young ones, we may stay very much at the engage, notice, wonder stage and not move too much further. With the slightly older ones, we get a little more sophisticated. We can move through this learning cycle. But this is not terribly different from what happens in a science class, if it's a good one, all the way up through the learning, K-14, 16, 18, whatever. And in some interesting ways also reflects what scientists do when they're exploring or something new or some question that interests them. So it's a touchstone, it's a scaffold. Any kind of exploration is far messier than that. This is very linear, it's clean, it's two-dimensional, it goes from top to bottom. But the arrows are to suggest, yeah, we circle, it's not quite as clean as this. But what it can hopefully do for some of you as teachers is to think, when I'm thinking about doing something in science with my kids, am I thinking about a process? Am I thinking about just an activity, or am I thinking about a process? And this may help in thinking about a process. And of course, in the meantime, there are lots of skills that are starting to be practiced. And here's others. I've got more. This is the beginning of the list. Kids are raising questions, they're exploring, they're making observations, they're describing, sorting, classifying, all those things that we're supposed to do. Using tools, maybe as simple as using a little magnifier, and so forth. Working collaboratively, sharing and discussing ideas. If we do this, if we engage in this, and my bias, by the way, I'll say it right now, is we could do science all day in classrooms and we would be able to touch on everything. But I don't necessarily believe that to be quite true. One of the interesting things that I wanted to also just put up there, I think this is in the handout, I'm not sure. There was a recent issue of Exchange, is that what it's called? The early childhood email, web-based newsletter, in which, since I don't remember her name, I'll just check it here and come back to this. Jane Healy, in her book, Your Growing Years, talks about the characteristics of creative people, not science, by the way, just creative people in general. And this is her list. And I grabbed it and took it out of there because I thought we often think about science as kind of rational and logical and so forth, and something rather stern about it. But if you look at least this person's list of what makes for creativity or creative people, I look down the list and I say, well, if kids are doing inquiry science, if they're really exploring science from a perspective of inquiry and investigation, this is what they're doing. They're usually very absorbed. And even some of the children who give us more trouble than others can be quite involved. Patterns, relationships, combining things in new ways, challenge each other, coming to decisions. And these sound very highfalutin for very little kids, but I think they're important. And I think it's important for us to see where science extends well beyond what some of us may have learned science to be as we went through science courses in high school and even science courses in college, that it's a very mathematically logical, cold memorizing of a lot of facts and information. But it's really all this, too. And for our young ones, for the little guys, this is where I think we want to think about how this helps kids develop some of these other skills and attitudes and habits and ways of thinking. Now, I did get sent and looked at the Iowa Preschool Learning Standards just to see how does all this connect, and does it? If you have to obey the standards or teach to them, then we have to look at them. And we're all into standards these days. So I just went through, I'm not going to read them all, but I looked at the standards for approaches to learning, curiosity, initiative, engagement, persistence, problem solving. I said, okay, we can do that in science. Science is going to help us with that. Here's math and science. Only a couple on science, but nonetheless, math, of course, doing science is full of mathematics. We're certainly, if we think about this sort of inquiry-based science, children investigating and solving problems, observe, describe, predict the world around them, we're certainly following or trying to move forward towards these particular standards and goals. Social and emotional development, build out a couple of those. Communication, language, and literacy. Creative arts. So I think when we're doing science, when we give time to science in the early childhood classroom, we're really meeting a lot of these standards at the same time. We're doing double duty. So it's not an add-on, it's really an opportunity to come at what we are really being asked to ensure our kids have the opportunity to do, and to ensure that, and to allow them to do it in a pretty exciting and interesting way. I don't like that slide, I'm going away. So if we think about science as a process, that inquiry process, where kids go through that learning process, the next question is, what is the content of it? What subjects do we teach? What content, what ideas do we teach? And I never make a list, because I don't think it is about a list. I think there's lots of choices. I mean, if you think about the world, even in classrooms, and then the world outside classrooms, there's possible science there everywhere, stuff to build on. So instead I have a list of criteria. As I look at what might be possible to pursue, I think, is it interesting and engaging? Obviously. And by the way, is it interesting and engaging not just to children, but to me? I think as teachers, we have so much choice as what we can pick up, what we can use as the subject matter, the ideas of science to study, that we're allowed to say, well, I'm really excited about ... whatever it is. Or I think that's really interesting. It's interesting to the kids, so let's do that one, because your enthusiasm and your interest is going to give them, you're going to share that. Whereas if you hate insects, don't study them. Don't have that be the focus of investigation. Choose something else. It draws directly from children's experiences. Now, I'll put the two together, can be explored directly. There are certain things that those two criteria eliminate that often appear in classrooms. Dinosaurs? No, doesn't fit that criteria. Penguins, polar bears, doesn't work either. Rainforest, doesn't work either. We want to think about the things that are really in children's experience. If we want them to explore directly and to go through an inquiry process that builds from experience with the phenomenon and so forth and so on, straight through to the end, it's got to be there. And not in pictures, not in images, not on TV, not in the media, but there to be studied, at least to begin with. Now, you might do a lot of studying of what are the characteristics of earthworms, where do they live, how do they protect themselves, what are their basic needs, and then we might look at polar bears and say, how different are they? But it's not because we're studying polar bears, it's because we're studying the behavior of living organisms, their basic needs and how they meet them. And we're talking about habitat. We're talking about a bigger idea. And it's got to start there. Is open to deep exploration over time is another one of my criteria. I think, and I think many of you have been in child development classes, you know that children that encounter phenomena, can counter things, experiences, in lots of different ways to begin to understand them. They need to have multiple entry points, and they need to have experiences over time. So we have to think about things that allow that. And my example here is magnets. My counter-example. Magnets are fun, and they stick to things, and I can stick them to things, and I can find out what they stick to and what they don't stick to. But sort of once I've done that, I'm done. There's no depth to pursue, because magnetism is a really hard concept. So while it's great to have magnets in the classroom, they're not the focus of my science, because it's not rich for young children's explorations. It's perfect. Studying magnetism in high school is tremendously rich, but not so much at the younger levels. So that goes through my mind as well. I think it's important that the concepts are important. Doesn't matter what their ages are, there are basic science ideas that we can work with and that will provide this foundation of experience for later years. And then it's developmentally appropriate. And that's defined very differently by different folks, but obviously at least minimally what we're asking here is that the ideas and concepts are accessible to children at the ages we work with them. So, here's an example. If I go now to life science, which is an area that a lot of people work with young children, and I think about, okay, what are those ideas that matter, that are important, and that also can be studied in the existing environment? Well, here's some of them. We can look at the characteristics of living things because we have living things all around us. See, we have one example at least of not quite the age level we're talking about, but almost. Living and non-living. The needs of living things. Life cycle, diversity and variation. We're not all the same, but we're the same species. There are many different species. The idea of habitat. Interdependence. If we see organisms outside and we study them, those snails are dependent on some plants outside to survive. The worm is dependent on soil that it can get into, and so forth. So these concepts are in my head, or some of them, I pick some, when I think about what's a good piece of curriculum that I want to focus on. If the kids got really intrigued by little critters outside, and we wanted to, and I thought it's important to do some of this, I might decide that I'm really going to focus on characteristics of living things, their needs, and their life cycle. And that could be the focus of the work we do with lots of different little critters outside. I could choose something. I could choose plants instead, for those of you who don't like little critters. We can go for plants and look at the life cycle of plants. But in each case, I'm starting with an idea, and then I'm looking at what the environment provides me, or I put into the environment that allows kids to explore that through this process of inquiry. Now, life science, which many people do more of than physical science for a variety of reasons, we're more comfortable often with life science than physical science, has some interesting, if we think about how we study living things. In the younger grades, we're not talking about experiments with living things, really. We're talking about looking at them and watching them in natural conditions, outdoors maybe, and something we bring indoors. It takes place over an extended time because we have to look carefully. Growing takes time. Seasons change over time. That's hard with young children, to keep that moving and to keep them going in looking at living things as they grow and change. So while a lot of what I see in the early childhood classrooms is around life science, because teachers are often more comfortable with it, I really like the physical sciences because things change. You can bounce balls, you can roll things, you can fly kites, you can play with water, you can do all sorts of things in physical science because the phenomenon is not alive, and it moves quickly. So you have a different kind of science. The other very simple thing I do often when I think about curriculum is to say, okay, if I want to study living things, and I think those concepts are important, and this is not a concept map, this is much more simplistic than that. It's simply, where are those things around me? Where do I see them? I can see, if I'm thinking about living things, this is just 4. We could put 6 more up here. But it's a way of saying, how do I connect these big ideas to the world children live in, and where are the various places that these might be? And you can play this game as you think about, what is it that I want to study, and where is it in the environment nearby, in the classroom or outside the classroom? Let me show you a little story. This is to remind myself to do this. I want to show you just some images, so this isn't all words. This is a Head Start classroom in Boston, and this is the class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There were about 18 kids or 20 kids in this classroom. It's a 4-year-old Head Start classroom. I think in this classroom, out of the 20-ish kids, there are about 14 different languages. So a wonderful variety. And they started a project on living things. And this was the teacher's decision. We're going to focus on living things. And we're going to see what we can find out about the living things, particularly the animals. But she hadn't quite decided that before it started. But particularly the little critters. And so the first step was, in this open exploration, was simply to go outside and say, what's there? And you can see they were fortunate. They have a part of the area outside the classroom was rather wild and untamed and surfaced and so forth. So the kids are just looking. And of course, you know that if you look under rotted logs and things like that, you find things. And they looked underneath the boxes that were surrounding this little garden they had done. And they started to find things. And more things. This was a process over time. They went out once, they went out twice, they went out a third time, looking for what's out there, and coming back in and saying, we saw this, we saw that, we saw the other thing. They looked at what they saw. They brought out the tools of science, the simple tools, and this is one of them. It's a magnifier. They also had those little bug boxes that you can put things into that are closed so they don't run away. And then this little girl found a snail. You can see it there. And that produced quite an uproar, needless to say. And so the teacher decided, helped them to decide that they could bring the snails inside and look more closely and see what they could find out about the snails for a brief visit in the classroom. So they brought the snails inside. This is a little bit out of order. This shouldn't be, you'll see why. But anyway, and one of the things that they did, because it's very important in science, is documentation. This is a snail, obviously. At least it's the main thing about a snail that a very little kid is going to see, and that's that a snail is this. And this is another snail. These are very young 4s, possibly 3s, but I don't think so. I made a shell, house, made a door, and me, I live there. I mean, you hear this. This is the mixture of fantasy and reality. But it is this notion of house, shell. There's another one. What this teacher had done, of course, was when the snails came in and were in the classroom to be observed more closely, she had all of these recording areas, these areas in which the kids could document what they were thinking and looking set up. The paint area was devoted to snail paintings. There was large chart paper with crayons. Now you can see those snails. One, two, three, or 1, 3, 3. So lots of documentation, lots of recording. Now, these may eventually, as you saw with the earlier ones, they don't look a lot like snails. These are getting quite respectable. But what's so wonderful about this documentation is that in order to do anything, you have to look closely. So the purpose of this is not to produce a product that is a snail, but rather that kids actually try to think about what's important about snails. The product, maybe, but that's not, it's really the process of getting there that is part of this collecting. This is data. This is collecting of data at a very young level. You'll notice here that Again, we're getting pretty sophisticated. Look what they've noticed in this particular child. Different sizes, and the antennae and the eye. Again, this is a pretty good representation. What's important is that having been asked or encouraged to represent, they're noticing these details that they might or may not have noticed before. The kids kept going inside and outside. It was part of what the teacher was trying to do, was helping them see that by going outside, we can see what the environment and habitat looks like. By coming inside with the snail, we can look very closely. But then we have to go back outside and again see the answer to some of our questions about where they live. Can we find others? Here's another documentation of the snails. This is one child's documentation, another form of documentation panel. And this one's interesting in a variety of ways. One of them is the movement from top right down to the bottom left, where you see this child working to get more and more of the detail. It's still got a smile, but that's okay. But the head is actually there, maybe that's a foot, where he started with just circles. And even labeled them circles, although it was focused on the snails. The kids decided that they wanted to have a home for their snails inside. And a teacher said, yes, we can make a hotel. We're not going to keep them because we don't know how to keep them well, and this isn't their home. But we'll see what we can do to make it a place they can be comfortable in. What is the teacher thinking? The teacher's thinking habitat. What is it that is important to meet the basic needs of snails? Remember that list of basic concepts. We're looking at basic needs and how to meet them and habitat. So this is the kids' list of what they would have to put into their snail vivarium. Some things that they had seen outside, some things may have come from something else. And this is the documentation panel that the teacher did with them to make the process of creating it visible. And you can see that it's pretty messy, but they worked their way through, and I think I have the other part of it. And they put their snails into it. So now they had, by creating this vivarium, think about the thinking of the kids. They thought about what they looked like. They thought about where they come from. They thought about how they might meet their basic needs. Now they've actualized it in a vivarium, and now they're going to keep them for a few weeks and then take them back out again. They're not going to stay there. But as far as the teacher is concerned, she's got these big ideas in the back of her head that she's moving forward with. And this is somebody else's individual documentation of the vivarium. Now, once the snails were inside for a while, and they would take them out and put them on surfaces, teacher noticed that the kids were particularly interested in how they moved. I mean, how do snails move? Do they have 1 foot, 2 feet, 3 feet? Is that a foot at all? What makes it happen? My snail weighs like 100 pounds, eats all the time, da-da-da-da. And my snail, zigzaggy lines, that's where the snail goes. So the teacher decided, as she's listening to all this, that what she wanted to focus on, that one of the question the kids were asking here was how does this thing move? And so they embarked on a study of how the snail moved. And after watching them and having them on tables, on plexiglass and so forth, this was the result of one conversation, a lunchtime conversation. It's not bad. They walk with 3 feet is a little off-center, but they do go very slow. They walk fast with lots of feet. These are all interesting ideas that came out of the kids. This is simply their words. There was no attempt to try to make this real or not real. Look at the language, by the way, and the observation and so forth, and the thinking. I mean, it's clear that this is a problem. Another thing they did was to track the movement of the snails because they were interested in it. And you can see they followed the snails with a magic marker as they walked around or whatever they do. Here are a bunch of snails. You can see the starting points and went to sleep points. Okay. So we get a sense of their kids' interest in their movement. So they went out, they searched, they looked at the environment, they found an animal. The teacher encouraged them with these ideas of thinking about these big ideas, these basic concepts, and then it's all done now, and the teacher wants to move on, in this case moving on to a study of worms to contrast, because compare and contrast is a wonderful way to highlight what goes on. But they did stop. They did sort of consolidate and bring closure to their work with snails. So have a body, 1 foot, and it moves, a muscle. They walk around and around, indeed. The problem is that snails walk with 1 foot. Somebody's problem, at least. Now we're into reproduction here. They kiss and they dig because they want to put the eggs inside, and then they put dirt inside. No idea where that came from. Neither did the teacher, but there it was. Meeting basic needs. You notice this reflects that chart of what the snails need. And then they went back outside. So there's a little story line of thinking where the teacher takes some interesting concepts. I'm sorry I don't have the worm story for you, because it went on to a rather similar story about worms. And one in which the kids, I never know how to do this. There must be a way, but I'll just do it this way. Where the teacher went through with them a very similar pattern so that they could contrast them. Where did we find the worms? What do we need to have for the worms if we want to bring them inside? What do they need? How can we create a mini habitat? How do worms move? Do worms move like snails? Don't know. And then letting them back outside so that they began to think about how do we study animals. We think about these behaviors. We think about what they need. Now, here's just a quick other example of of a whole other concept of physical science. Just to give you, again, what do I mean when I say big ideas and concepts? Well, the big idea with water, the physical science concept, is properties of materials. Basic science concept. We also have science, then we have the basic properties of liquids. And then we have water. Some of you heard this earlier today. So if I'm thinking about water and kids as a teacher, I think, what are some of the ideas that kids can really explore? Some of the concepts. I'm not going to teach them, but what can specifically or explicitly? Well, water flows, takes the shape of its container. Boy, can I do a lot in the water table with that feed those ideas. Tubes and basters and things like that where kids can make water move, hopefully staying relatively much in the water table, but nonetheless that big sort of water. I can also fill and empty the juice cups. I can turn on the faucet and see the water coming out of the faucet in lots of places. Cohesion, adhesion, not teaching those words, not teaching the explanations, but when I have little drops of water with pipettes, they're round or domed on a surface. That's because water does this funny thing. Water actually sort of has a shape when it's in a tiny quantity. It's a drop, it's round. So we can play with a lot of drops and see what water does. When you have drops on different surfaces, cohesion, adhesion, what happens? When you put it on a paper towel, it spreads out. When you put it on the tablecloth, it spreads out. When you put it on a piece of wax paper, it's round. When I put it on my raincoat, what does it do? Depending on the raincoat. So what does it mean to be wet? It's wet when it spreads out. It's not wet when it's in a drop. So we can really play with drops in lots of ways. Drops on the window, drops outside, drops on the side of a cup. So lots of tabletop activity around drops. That takes us out away from the water table. Now this is another table. We're not doing science tables, we're doing water table. Objects sink and float in water. We can have another table where there is a little container of water and see what sinks and what floats in water, and what happens if what kinds of things do we put in, and so forth. We can approach the study of the behavior and the concepts and the properties of water by having water play in multiple places in the classroom. And this is why I've said a couple of times, I don't know if I've said it tonight, no science table. There isn't such a thing as a science table. There's an investigation of different concepts, so that science may be living things on different tables and on the windowsills. Science may be water things going on at several different tables. The only science table we have is a shelf with our tools, magnifiers, probably measuring tools, that kind of thing. But this idea we have of a science table, we want to shift our ideas, because it's really a science investigation. It's a science project, and it doesn't sit on one table. Well, that's snails. And, I'm going backwards again. One of the reasons I love the physical sciences is because it's so responsive. So I won't go over this, but just if I think about physical science versus life science, I'm ready to do physical science most of the time in the early childhood classroom, because it's so responsive to kids, and it happens so. There's so many things you can do and experiment in short periods of time. Again, if I want to think water, I can think this way, but I would build a much more complicated one. Now. What's our time frame here? I forgot. I don't want to. Another 10 minutes or so? Okay. Let me tell you one more story, not about water, but about a physical science. And because I like this one too. This is about a science study of building structures. You all have block corners. You're all in classrooms where there probably are blocks and things to build with. So that's a great physical science study, is what do we do with, what makes things stand up and why do things fall down? Either way, you want to ask that question. Lots of physical science in that one. Here's some of the concepts that are involved with simply thinking about building things. Lots of forces. And mind you, it's good to know what these concepts are. You don't have to be a PhD in physics, however. But you do need to play with the materials so that you know what the materials can do. These are here to guide the thinking a little bit and the thinking of curriculum development. But you're not about teaching kids these concepts. You're about providing the experiences from which they can begin to think about some patterns, connections, relationships. Gravity is really pretty complicated, but at the level of the children, where we're actually at many people's level, it's that sense that, what is the kid, that one over there on the floor, who drops something off the edge of a high chair all the time, just drops it and you pick it up, drops it again, you pick it up, drops it again and you pick it up. Well, what they're working on is, will it always fall down? Because once I'm sure it'll always fall down, I can move on. It's become predictable, it will. And then if they drop it, it's because they simply want to they're taking you out for a trip. That's a different story. But it is this investigation. It is this sense that, okay, now I know the world is predictable, at least a small piece of it. When I let go of something, it will drop. That's gravity at this point. And water will go down. And if I roll a ball down, if I put a ball on the top of a ramp or on a flat ramp, it won't roll. But if I tip it, it'll roll. And it'll roll in the direction of down. Interesting little clip that I saw in the work that Betsy Zahn at the University of Northern Iowa was doing with ramps and balls, where a little 3-year-old had a ramp. And He wanted to roll a marble down the ramp into a little container. That was his goal. He had a problem. He wanted it to get there. And he has the ramp flat, and he puts the marble on it. It doesn't do anything. And then he puts one end, pot's over here, he puts this end of the ramp on something, and it rolls the wrong way, because it's going towards my hand here, not into the pot. And he tries it again, and it still goes in the wrong way. And then he turns it around. So it's still tipped in the wrong way, but he thinks maybe if I turn it around, it'll go where I want it to go. And then, finally, after about 3 or 4 or 5 minutes, he actually tips it the right way, and it goes in. And then he does it about 3 or 4 or 5 times, and he's done. Figured it out. But it's one of those rare moments where you can actually watch this going on, where you can watch this experience going from one piece to the other. So these kids were playing, again, exploration time, that beginning of inquiry. We're going to do a whole lot of just all sorts of building. Big blocks, other kinds of blocks, waffle blocks, those connecting straws and Kapla blocks, those rectangular ones. More Kapla blocks. Notice tables, block corner, all over the classroom. Not quite all over, but in many areas of the classroom. More Kapla blocks. Notice the recording documentation going on right there. That's another tool of science, the clipboard and the pencils. Yeah, we're proud of it. The block area, of course, and in the back of the block area you can see lots of documentation, hard hats, because if you can't build tall, why bother to build? It's much more fun. And in this case, the kids did start to build tall, and you know that this happens at a certain point in the classroom. Rather than building flat, they start to build tall at a certain point. And so tall became the focused exploration. How do you make tall towers? And what do you need to do? Well, one thing is you need to wear a hard hat. The other is they have to stack very carefully, otherwise it doesn't work. So which blocks make the tallest towers? And yes, they're standing on chairs, but they were fine. But notice, these are 4s, same class, Cindy's class. This little one was not interested in the big block area. He was very happy to do his building on a small table. There again, science is not just in the science area. It's in many places. He was just as happy with this as those 2 boys on their chair. And he's dealing with the same concepts and the same structure. This is probably engineering as well as, of course. Using the straws. Can these make the tallest one? How tall is tall? Math. Well, it's as tall as my knee, or not quite, for this little girl. Now it's getting to be up to my waist, even though I'm a different size than the other one. That's okay. How strong is my tower? Of course, that's part of a structural. How do we build something that doesn't tip over when you blow on it? 3 blows was the measure. How can I represent my tower? I can take a photograph of it. Notice this is Lynn's tower photograph, and that's her collage model of the tower. Pretty sophisticated for a 4-year-old. You can do it in clay, but actually it doesn't work very well. So we've got an interesting, what kind of structures do you make in clay? This little girl, interestingly enough, for this age, had drawn that outline of her tower first, her architectural drawing, and then was building her tower to fit. You think about the thinking process going into that, from this is what I want it to be in 2 dimensions, and now I'm going to build it in 3 dimensions within the framework that I did. That's pretty elegant. Documentation, right, left, and center. The digital camera is your friend in this. Notice the kids documenting as they build. And this was the experience chart, the documentation panel that came out of this focused exploration of tallness. Which blocks will make the tallest? And Notice again, the winners, by the way, you can see it was as tall as the teacher. Not quite, but almost. But again, you notice, just like with the snails, that there is a closure and synthesis of the understanding that takes place. What did we learn? You have to put them right on top of the other. The tower stands better if you build it on the blackboard instead of the rug, and that's a blackboard laid flat, obviously. Sometimes you have to move them back and forth so the tower will stop tipping. Think about that feel of balance and symmetry. It'll stand up better if you put some more blocks right next to the tower to hold it up. Well, now we're building cathedrals with the flying buttresses. But that synthesis, that's what we're after, and that only happens when the kids have all this experience, and then the teacher comes with them to the reflection and thought and reasoning on what they've done so that it becomes something more than just we built a tall tower. Look at that. I counted 35. There really are 35. More documentation. Okay, and I'm going to stop in about 2 seconds. And if I do, let's see, maybe I can do this right. Oh, I don't think I can do this. It's going to start from the beginning again. Somebody later on can teach me how to do this so that I can get to the slide I want. In the meantime, you're going to have to bear with me. Okay. One way to think about, just sort of wrapping this up, there's more on your handout, by the way, but I'm not going to get to it. As you think about the science in the classrooms and you think about what's going on here, this is just one way of thinking about it. On the left, with the less emphasis, is a list of things that we tend to do in early childhood science classrooms when we're doing science. And so what I'm urging from all of this is to move a little to the right, that instead of the individual activities, this week we do an activity on Wednesday and another one on Friday, and demonstrations, inquiry and investigation over time. Facts and information, no, we don't really need a lot of that. That's not what it's about. It's about ideas and theories and that process. That's where we're moving. Experience charts, where we just write what the kids say, yeah, those are good. But we also want to move towards science notebooks and documentation panels, children's work and drawings, and so forth. You can see weekly science themes or topics, no, longer, if we can, a little longer each time. Books as the source of information, great to use books as motivation and enrichment, but let's really have the firsthand experience. Science talk is show and tell or sharing to really, and I do mean this with the little ones, not the infant toddlers, but the little ones. Discussion, debate, and sharing. You know, what did you find out? Did you find out the same thing? How come you didn't find out the same thing, the two of you? Better go back and try it over again. Or what do you think about that? That's different, what you said. So the kids begin to build on, or you did something very interesting. Can you tell us about it? Now, did anybody else do what she did? So the children begin to not just single-mindedly share or answer my questions, but they begin to sort of approximate what we would call a debate, or even sometimes the older ones an argument. And you can see, when we pick an area like the water table or the blocks or so forth, to really think about it, at least for a while, as science, with a science lens, and then it can go back to being something else. But for a while, if we're studying water, leave it that way. And, well, I'll leave you to read the rest of your PowerPoint handout, which has quite a bit of other stuff on it. But this is something that I like to either end with or lead into the next section. Today it'll be end. And that is a quote by a different George Foreman than you're thinking about right now. He's a wonderful early childhood science educator who used to be at the University of Massachusetts and has worked closely, for those of you who recognize the word Reggio Emilia, has worked closely with the folks in Italy. But this is something I think as early childhood teachers we need to remember, because we know about experience. We know that experience is what kids need at the core of their lives in the classroom. But they have to be encouraged to think about it. We have to facilitate those discussions, that documentation, that argumentation, if we really want to make the experience educational. They'll explore and do the experience themselves. They're not likely to take it further and push their thinking unless we help them. And we help them by how we talk with them when they're working, how we talk with them in small groups, how we talk with them as a full group, and with all that documentation that we do. So I'll leave you with that. And then, if you have any questions or thoughts, happy to entertain them. Do you?
And can you talk more about the intersection between creativity and the science concepts, where the kids can move freely back and forth between imagination and reality, and how to deal with that so it's most effective?
Good question, and I don't have a good answer, of course. But if I were to think about it, I think that there are two different kinds of creativity I'm thinking about when I look at that list, and one is the kind of imaginative, magical thinking that kids will often do in their play and in the work they do. There's also the kind of creativity that says that, oh, I wonder what would happen if I try this. That's sort of way out in left field. Or this is kind of like that, where they're bringing two things together that you as an adult would never think they'd bring together. Or they are sort of making a connection that's unusual. Or they are creating a story out of what they've discovered. And the part that intrigues me most is how we build that kind of creative thinking still within the real, not into the magical and imaginative in that sense. I tend to pull kids back from the magical when I'm not fiercely, but if there is those wonderful smiles on the snail. Now let's see, I'm trying to find, is the snail really smiling? Can you tell me about that smile? Because I'm actually wanting to see what the snail really looks like. I'm actually wanting the child to look closely at that expression, listen to me, expression, the parts of the face rather than off into something that's detached from it. There may be other ways of thinking about it, but I think about the creativity more in terms of the creative thought and how we put it together than the magical. That's a distinction, and I don't know if it's valid. I just know that that's the way I think about it. Anyone else? You just got all those hungry people who left without eating your food. We should have told them to pack. You should have stopped them. Made them go back. Anybody else want to jump in?